Hello, and welcome back to Quantitative Reasoning Online. Today we'll be starting a new learning plan 6. And we'll start with lesson 14. More statistical studies, part 2. Specifically 14A, 14B, 14C, blood pressure and bias, taking aim at bias, and conclusions and observational studies. 6. Wow, that means we're almost done. So let's look at the preview assignment. Let's size her up. And let's see what we're going to do today. Well, it looks like we want to understand that error is an estimate. In an estimate has two components, a sampling error and a non-sampling error. We will determine when a sampling process can yield non-sampling errors due to bias, and we determine the median and the mean of a set of sample values. So median, the middle value, mean, essentially the average value. Remember, this is from low to high, and is the middle value. This one, we're going to add everything up and divide by how many. So, little differences between them. Sometimes they're very close. So let's see, in the next class, you will continue to explore population and sampling and learn more about error. Specifically, error that arises from reasons other than sampling. One primary source of error is bias. The tutorial for the preview of lesson 14, part A, blood pressure and bias, begins here. Recall from lesson 13 that sampling error occurs when statistical characteristics of population are estimated from a subset or sample of that population. Since the sample does not include all members of the population, statistics computed from sample data, such as mean or median, generally differ at least slightly from the parameter value for the entire population. Bias occurs when some flaw in the design or implementation influence the measurements that are being taken. Bias, flaw in design, implementation, influence measurements. An important measurement that medical professionals use to assess the health of a patient is blood pressure. The device used to measure blood pressure, therefore, should be reasonably accurate with little bias or error. Means from samples, such as average blood pressure, tend to have some error and differ from the population mean. If researchers need to estimate the mean blood pressure of an adult, which of the errors below cannot be avoided? All right, hang on a second. Do this again. If researchers need to estimate the mean blood pressure of adults, which of the errors cannot be avoided? Error. A. Errors that arise just because researchers are using samples instead of the entire population. N vice N, and typically N is much smaller than N. Errors that arise because the samples are not representative. Okay. Basically, you have a high number of people with high blood pressure? Sure, let's take all samples of people as they come in and out of a medical center. Errors that arise because the measurements are being influenced by the way that researchers are measuring them. Errors that arise because the measurements are being influenced by the way that researchers are measuring them. What's an example of that? If you ever had your blood pressure taken, you know they kind of like jack up the cuff or pressurize the cuff. No, you should have your wrist or you have your arms about heart level. Feet on ground. So a major researcher has found that, you know, if I have everybody have feet propped, that may influence the blood pressure. If you have your arms above heart level, okay, no, that's going to influence the blood pressure. So which of these can you not avoid? Can we always ensure a good practice is used in measuring? Yes, we can. So this can be avoided. Can we ensure that we have representative population being sampled? Yes, we can. Can we avoid the fact that we're using a sample instead of a population? No, we cannot avoid this one. So A has to be the answer. And here's an explanation for B and C are ways of inputting biases into the results. Bias is not good. Bias is bad. So, when using a measuring device, we have to take care that the device is calibrated, which means that the device is working properly and providing accurate measurement. If not calibrated, then it may indicate measurements that are consistently too high or too low. This type of error is an example of, okay, so if we're consistently getting our samples too high or too low, okay, that's putting in an offset. Offset is also known as bias. Remember, sampling error is basically using a sampler's population. Bias, B. See, sampling error is error introduced by using a sample rather than population. N versus N. Like I said, N is typically much smaller than N. Having an inaccurate measuring device is an example of bias. Most of us had our blood pressure measured. Newer devices have been developed that can measure blood pressure by simply attaching a cuff to a person's finger. Wow. Research carries the blood pressure indicating including systolic and diastolic reading. I believe this guy is your upper pressure, and this is your lower rest pressure. 120/80. Yeah. Write a few sentences in your own words. I'll leave that up to you to do. Okay, the finger cuff device was used to collect the systolic blood pressure. Okay, I always gotta look at this one. Okay, systolic. So systolic, this would be the upper, or basically the pressure that the heart puts out when it contracts. So here's numerical data. And the question is, what is the median? All right. Now, ideally, for the median, we should be able to rewrite this from lowest to highest value. And it looks like the lowest starts at 103 and goes to a high of 133. And you got to plot them out, figure them out the rest of the way. How they did give us a dot plot. We know that n equals 30. All right. So the median would be at location. Let's see, 1/2 of 30 is 15. That's a whole number, so we need to look at position 15 and 16 and basically average them together. So we need to find the 15th and the 16th number. Now if they gave us a dot plot, which is in order from lowest to highest. 103 would be the first position, and 133 would be the 30th position. So let's look at what's 15 and 16. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it looks like X15 is 119. X16, or the 16th value, is 119, because they're on the same column. So the average would be, well, 119 plus 119 over 2, 119 inches of mercury, or whatever the heck is measured in on those guys. Now, just for argument, say as we were counting, we found it was this one and that one. That was the two numbers. That was X15 and X16, or 15th position and 16th position. In this case, would have basically been 119 plus 120. Or 119.5. But that green's not the case. Red is. Okay. Remember, we counted out and we found it was it was these two we found it to be. That was just a what if. But with a dot plot, you can use the dot plot as your counting tool to find out where your middle number is. Between 15th and 16th value, since both 119, the median is 119. So here we go, 15th and 16th value, 119. Get it? Got it? Good. Now, what is the mean of the pressure? Now, with the mean, I'm just eyeballing it. So when I eyeball it, we can see that there is pretty much a symmetrical around that middle area. So if I had to make a guess, I would say the median would be on the order of 119. But we don't. So we truly need to add them up. So let's see what we got here. We have a 103, got 112, 113, 114, 116 times 2, 117 times 4, 118 times 3, 119 times 1, 2, 3, 4, 5, 120 times 3, 121 times 3, 122 times 2, 23, 24, 125, 127, 130, and 133. Do some easy math there. That's 360, 363, 244, 232, 4 and 7 is 28, carry the 2, that makes it 6, that makes it 4, 8 and 3 is 24, carry the 2, 3 and 2 is 5, 3, 5 and 9 is 45, carry the 4, 5 plus 4 is 9, 5. So, let's add all those numbers up. $103 plus, and I'll add them up. Okay, you need to watch me all that. All those numbers add up to 3,573. So I take all that, divide it by 30. So we get 119.1 as the mean systolic blood pressure. Notice instead of adding all of them individually, I kind of used the advantage of the dot plot. It was telling me for each pressure how many I had. Of course, these are just ones, and just did that. 119.1. Right on. More power to you, baby. Oh, okay, that was done. So, how confident are you that you understand that error as an estimate has two components, sampling error and non-sampling error? Call sampling error the fact that using N versus N, a sample versus population. Non-sampling error is essentially one methodology, a bias, doing it incorrectly. How confident are you that you can determine when sampling process can use non-sampling errors due to bias? Oops. Pretty much confident. Somewhat confident. And to determine mean and median, oh, I'm good at that one. So should you. All right. Next one, here we go. So let's see. We looked at the two types of sampling errors, or sampling, non-sampling error. We looked at what can cause bias, and median and mean of a set of data. All right. So that completes for a tutorial, and I'll see you shortly for so go back and do it again yourself to get the credit for it, whole 1 point. But again, just to verify that you know how to do it, and I'll see you shortly for the questions.